Hi, I'm DJ Ware. On this episode of the Cyber Gizmo, I want to represent the file system benchmarks as I do usually 6 months. I'm a little late, mainly because I've been working on a system to automate the benchmarking process. So I have been hand coding in Python mostly just to prototype it, make sure that it's working. But it saves me about, well, let's see, usually takes about 2 days to run the benchmarks and then produce the charts for these videos. So this, hopefully will shorten it. This is my first run through, so there may be some errors or maybe some problems with it. I still have a couple of more features I want to add into this, but this is fully scripted. There is no AI in this. This is HI. This is me, human intelligence, writing this code. So yeah, anyway, let's get started. What did we test? I'm testing Bcachefs, and there was a little bit of challenge in getting that running. I spent a couple of days this week trying to make sure that that was working correctly with the version of the kernel that I had. And I'm also retesting Btrfs. There have been a lot of claims for performance increases over each of the successive major kernel releases. So I want to check that out, make sure that we capture its new performance guideline, its new performance, if any. And then ext4, of course, we want to test that in XFS. Those are the two main staples, at least in my environment, and of course ZFS. I'm still trying to tame ZFS so that it does not use as much memory I/O as last time. So yeah, I am trying to make some changes to it. Now Stratus was not tested, and the reason is on the other chart on the right. So let's do that first. So I ran all tests on hardware. I used a single distribution of Linux called Bcachefs. This is an Arch variant. I did not tune the file systems whatsoever, and I'm using IOzone 3 for the benchmark. Now, the reason why Stratus wasn't tested is Arch does not yet include Stratus. There's two parts, the Stratus D and the Stratus CLI. Arch does not have either of those, and I did check, it's not there either. So the reason why it was in the previous test was the base OS for that was Fedora. What am I testing on? I'm testing on this. This is an Ataman X7 Ti. It is a sub-brand of Minisforum, so they control the builds on it. This is an older one. It is a Core Ultra 9 processor. It's a 185H. It has 32 gig of RAM. I have one Western Digital SN850X, which is a 4 terabyte in this. The other drive, which is the system drive, is a Kingston OEM drive. But the Kingston's controllers are really good for the money. They're not the best, but they're really good for the money. So yeah. I'm running IOzone version 507. Now, if you go out and look, you might see that 508 is out. I looked at that and I thought, well, I could redo the benchmark. So I looked at the change notes, and the only change between 507 and 508 is they're fixing some weirdness that's going on. I don't know. Have you guys noticed that a lot of the development today is adding features that make absolutely no sense? So they're adding features to the GCC compiler that basically break all your bindings, and so that's what that version fixes. The other one is this is kernel 6.16.6, and probably by the time you get this, it'll be farther down the road than that. But that's what I'm testing on. Before we get into any further into this. That kernel is part of the reason why it took me so long to get Bcachefs running. I was complaining about it in the last video that at least on Arch, the package didn't include the module. Now, it's still in the kernel, in 6.16, you know that Bcachefs has been moved externally now to the kernel. So there are basically three settings in a Linux configuration for modules. They can be yes, which means it's built into the kernel. They can be an M, which means they're supplied by an external module, or they can be no, it's turned off and it's not supported. So in the case of Bcachefs, as far as I know, I think it's always been module, but I could be wrong about that. But it seems like I've always had to struggle with getting a module installed. The specs on the SN850, it's available in 1 terabyte, 2, and 4. The form factor is an M2 2280. It is a PCIe 4, and it uses all 4 lanes. The interface controller is proprietary to Western Digital, and I can tell you it is excellent. It is near enterprise grade. I'm not going to say it is enterprise grade. I'm going to say it's near. It does support up to 16 gigatransfers per second across all 4 lanes. It's a NAND type 112 layer BiCS5 TLC NAND. Its warranty is 5 years. That should tell you something. Operating temperatures from 0 to 85°C. Read speeds is, so that speed that's the maximum speed for 1 terabyte to 4 terabyte drives. It drops a little bit when you get into larger drives. And for write speeds, they say 6,600 megabytes. Random IOPS 4K is 1.2 million IOPS for reads and 1.1 million IOPS for writes. The initial write, let's look at some of the initial tests. Now, these are the output graphs that I am presenting. As you can see, yep, there are some problems. I have a little framing issue there with the ZFS that I'm not allowing quite enough room for spacing. I tested with the medium-sized file, 2 gig. In the past, I've used 512 meg, but I just feel like that in today's workloads of what we're using our machines for, it's probably more relevant to look at large files or medium files. But you can see that ZFS is clearly running beyond the drive's capability, and that is memory. XFS is pretty good. It's within range of the top worker of the speed of the drive, and so is EXT on writes, and Btrfs. It does okay on the writes. It's not stellar, but it does okay. Bcache has come up quite a bit from the last time I tested it. Let's go look at the next, which will be reads. So this is just sequential read, plain old sequential read. Both ZFS and Btrfs. It looks like the Btrfs guys looked at my benchmark and went, oh yeah, well, we can play that game of reading it out of memory too. Apparently, they did a little bit better job of reading out of memory, but they're in the noise. Those two are pretty dead even. So yeah, at least on my test. And then XFS, ext4, and Bcache are more true to the actual drive speed. So they are measuring actual drive performance and not memory performance. The rereads, this is just I'm rereading the file over and over again. So in this case, ZFS drops back a little bit, but it's still, at least from what Btrfs did, somehow they managed to push this to 40,000, which is even faster than standard memory. So obviously some of that could be in. ZFS is still running out of memory. It's 12,000 there on the top. XFS, ext4, and Bcachefs all do well, although Bcache struggles a little bit with the first worker node. But yeah, it doesn't do bad. The 512, by the way, on the title is the block size. So FReads, this is a stream read. I would say the winner here is Bcachefs in this particular way of doing things. Yeah, ZFS struggles a little bit to get its feet under it. But it is scaling up. All of them are scaling up really well. This is a big change from the past. Usually there was a file system that just fell apart. But ZFS will fall apart at the top. I think that's mainly because I do have a top level limit on how much memory it can take, because this only has 32 gigs of memory, and ZFS would be very happy to take it all. It only utilizes idle memory, so if you need it, ZFS will give it up. FWrites, this is again a stream write. This is the other end of the pipe. So this is the thing that stuffs the data onto the pipe as quickly as possible. In this case, this is where ZFS really shines here, is on this type. And then XFS, EXT, Btrfs, and even Bcache are running close to the drive speed. Although Btrfs is running a little over. Mixed workloads is kind of, read and writes that are going on to random locations within the file. So yeah, this can be impacted heavily by the system cache. You can improve this performance by adding disks to a RAID or improving your seek latency. Now that would only apply pretty much to just rotational media, like spinning Rust drives. Btrfs does very well in this test, but again, it's memory speed. ZFS is at the top end is memory speed too, but XFS, ext4, and Bcache are adhering to the drive speed. And these, by the way, are all supposed to be using direct I/O measurement, but ZFS and looks like Btrfs both ignore it, and they do whatever the hell they want. So PReads you'll find typically in C programs or C++. These kind of things are used to jump around in the file by a count of bytes. So it's kind of I've explained this before. It's kind of equivalent that you might have metadata that's in the front of the file, and so in the metadata will be a pointer to the start of the actual zip file or the graphics image itself, and so it'll hop directly to that part of the image to display it. ZFS and Btrfs pretty even here, again down in the noise, and that's memory obviously. XFS, ext4, I'm getting tired of saying this, Bcache, those are all doing just direct I/O, which is fine. That's perfectly fine. They all do very well. PRead, yeah, this is this is skipping around in the file to write data in the header or somewhere, to jump forward and then start writing the image. ZFS does really well here. EXT, XFS, Btrfs, and Bcache are all adhering to the logic of the direct I/O. Random reads are just like it says, it's random I/O. Bcachefs does, at the bottom is holding to the drive. Btrfs is some mythical amount of insane speed. It does very well on this test for random reads. ext4 and XFS, again, drive speeds, and ZFS. Well, up in the higher reaches, it's doing memory. Random writes, just random writing stuff to the file system. And this time, ZFS does well here, and the others, a little bit slower than the drive. I kept track of the temperature on this drive throughout these tests because I'd already killed 2 NVMe's. Didn't want to kill this 4 gig one. It's kind of important and kind of expensive. So it never exceeded 50 C, never during the test. That was the highest temperature it ever reached, which is that cooler on that Adaman is amazing. Rewrite, this test is it's rewriting a file that already exists, which means that usually that there's a lot less work required, and because you don't have to set up an inode table, you don't have to insert it into the directory structure and index it, blah, blah, blah. So ZFS is doing this in memory. XFS, ext4, Bcachefs is drive speed. Btrfs, drive speed. ZFS, memory. Reverse reads are reading the file backwards. That's pretty typical of compilers. We'll do that. Microsoft C Nastran is an example that does that. This one, the reverse read, Btrfs is, I don't know where it's finding this horrendous speed. But anyway, it is. It's 37 gig, basically, per second, which is faster even than the PCIe channel. So I know it has nothing to do with the drive. Yeah. So ZFS is at 12,000 XFS at peak, and XFS, ext4, and Bcache are all drive speeds. Strided read. This would be like a database would do this, where it has the ability to read uneven. You can change the amount of data that it reads on a single go. But what it means is, like in some databases, the index is embedded. There's a index that's embedded into the data itself, and so it'll look for those indexes to find the start of the file. And so we have ZFS, which is at 11 megabyte on the top. That's obviously memory. XFS obviously is direct I/O. ext4 is direct I/O. Bcachefs is direct I/O. And Btrfs is some insane thing that I don't know what it's doing. The Geomean is, I took all the test cases and ran a Geomean on them. This is what I came up with for that. This is on the medium size. You can see that Btrfs has 26.8% of the Geomean's share. So it performed overall the best on all the tests, followed by ZFS, followed by ext4, then XFS, then Bcache. So, yeah, I mean, consider where Bcache was last time. Wow, what a big difference that this is. Finally, what are my recommendations? So I'm still conservative. For a server, ext4 for the root drive, XFS for data storage drives. Workstation, the same now. You might consider Btrfs here for the workstation. XFS is still a good choice for data if root is ext4. I think ZFS really shines as a NAS file system. It has better redundancy. So if you're storing lots of data, you need the equivalent of RAID 5, RAID 6, then yeah, you'll need better redundancy there. So, and I would prefer it because of the rebuild time. If you've ever had to fix a drive that broke, ZFS's performance in rebuild is amazing. Plus the fact that it does a lot more data correction and data fixing than a RAID does. A RAID just isn't able to do that. So one comment that I'm going to make, though, is I hear this all the time in the comments from people saying, well, I'm going to use Btrfs because it has snapshots, and the other big reason is so that I can change, I can put in drives of different sizes into the array, and it works. It's fine with it. You can't do that with ZFS. There's a good reason for that. Did you think honestly that in 45 years that was an original thought? To be able to put drives of different sizes into a RAID? The three creators of RAID back in the mid-'80s actually did experiment with that. Did you ever wonder why there's RAID 0, 1, but no 2, no 3, no 4, and then there's a 5 and a 6, but there's no 7 or 8 or 9, and then you get to RAID 10. But you ever wonder why those others aren't around? It's because they experimented with that. They played around with trying to get the ability to take drives of different sizes. What happens when you do that is one drive is going to be larger than the other. That creates an imbalance in your RAID. That imbalance will echo in your reads and writes because they're going to favor the larger drive. In other words, most of your data and most of your, let's say it this way. There's a higher percentage of your data on the larger drive than there is on the smaller one. There's a higher percentage of parity data on the larger drive than the smaller drive if you're using a RAID to do that. So that imbalances things that you're going to suffer in terms of throughput, because throughput is an aggregate across all of the drives that are in motion, that are working together. So you increase throughput or bandwidth more correctly by adding drives in a RAID. That's how you do it. If you unbalance things by allowing to have unequal versions of the drive, you just threw your bandwidth out the window. Your gain from bandwidth is not going to be very, very large. So I'm not criticizing what you're doing. I mean, you're welcome to continue to do it. I'm just explaining that here's the reason why we don't do it. The second problem that you have with that is that since the larger drive holds more of the data and more of the parity data, it's also being hit harder. So its chances for failure are higher. The more you write is, let's see, the more you buy, the more you save. In this case, the more you write, the more you degrade the drive. So yeah, and that's just the case of things. So yeah, it will shorten the life on the drive. So and failures in a RAID is not something that's welcome if you've ever experienced it on one that's of any size. Yeah, the largest one I have ever seen was about it was close to, I think, around 800 terabyte. That's the sermon for this week. Thank you. The offering box. No, I'm just kidding. Thank you for watching today. I think that there was some real surprises in here. Btrfs's performance has come up. I would say they've done a lot on it to increase its performance. Now I wish they would fix their write hole problem, and then we could actually start using RAID 5 and 6. How they'll do that, I don't know. They've been working at that for some number of years, decades now. Let's see. And Bcache is looking good. It's starting to look like a contender for a good file system. And we'll monitor it and see how things go. Hopefully they patch up things with Linus and get all that straightened out. Anyway, that's all I had. Hope you enjoyed the video. Hope to see you all again very soon. Bye for now.